Hi everyone, myself Ria, and we would be starting off with the presentation for Infinity Hyperloop IIT Delhi. Next slide, please, Shivam. So, let me first brief you about the team, like what is Infinity Hyperloop. So, next slide, please. Yeah. So Infinity Hyperloop is a student Hyperloop team of Indian Institute of Technology, Delhi. And we were established in December 2021, not quite long ago. And we are a team of 35 plus dedicated students who are working on building a prototype for the Hyperloop technology. And along with building the prototype, our target remains to raise awareness among the people about this new mode of transportation and what it is and how it can benefit in us in the future and also to interact with other teams, and the experience has been great so far. So the vision is to obviously revolutionize the transportation system, contribute in what all of us are trying to do, foster the development of young engineering minds and promote research and innovation. And our ultimate mission remains to develop an autonomous scalable pod that can ultimately be realistically achieved in our country and in the world. So now let me tell you about the divisions in our club. So Infinity Hyperloop is basically divided into two parts. One is the business side of us, which is responsible for publicity, outreach, events, sponsorship. To basically raise awareness about this and to get aid and support for our team and join more people in this revolution. And then is the technical side, which is what this presentation would be mainly about. And our technical is divided into electrical and mechanical side. In the electrical, we have propulsion, levitation, navigation and control, and power subsystems. And in the mechanical side, we have brakes, chassis, vehicle dynamics, and aerodynamic subsystems. So now moving on to the departments, I would like others from my team to take over from here and start with the electrical side.
Hello everyone. I hope I'm audible.
Yes, yes,
So
Anjali, please.
I am
Yeah, you are audible.
so okay. So I am here to represent the propulsion system of Team Infinity Hyperloop. We have meticulously designed and modeled our first LIM as a testament to our commitment to revolutionize the high-speed transportation. Our motor boasts a contactless and energy-efficient design, providing the pod with a non-contact magnetic force for propulsion. With a linearly moving magnetic field, our LIM ensures fast acceleration while remaining seamlessly compatible with levitation systems and contributing to the efficiency and speed of our Hyperloop pod. Next slide, please, Shivam. So, as I explained earlier, that linear induction motor works on the principle of moving magnetic field, which is developed by the motor, which produces non-contact magnetic force over the system, which propel the pod. Next slide, please, Shivam. So basically, this is our first manufactured LIM, and you can see a testing video of our LIM, which we tested in our labs. So basically, we made it completely in our own labs. These are the different stages of manufacturing of the LIM. As you can see from the very scratch, like from to winding the coils. And next slide, please. Coming to the specifications of our linear induction motor, our LIM operates at a power of 1 kilowatt and has achieved a maximum speed of 40 meters per second, which is the synchronous speed of the LIM. We measured its thrust to be around 1 kilonewton. Next slide, please. These are some of the testing and simulations performed during our designing, which is compatible with the theory of LIM. And this is the testing video of LIM, which I guess have already shown to you in the previous slides. And this is the simulation video of how the linearly moving magnetic field moves. Okay, so our next task is we are currently working on the designing and manufacturing of a DC to three-phase AC inverter to power our LIM from the accumulator. We have completed the schematic design of the hardware circuitry and currently working on the PCB and PWM based control of the linear induction motor. Next slide, please. So basically, this is our power supply flow in our inverter. We are using two battery sources. With one is the high voltage source of 400 volts, and the other is 24 volts of low voltage source, which we are using to power our low voltage supplies like microcontroller and other low power units. We are also using an isolated DC-DC converter. So this was the propulsion system. Now handing over to the next department. Thank you.
Yeah, so I am Rishikesh, and I would be telling about the navigation and control department. Next slide. So the navigation and control department is basically about the communications inside the pod and also the communication from the pod to external sources so that we can control it from the outside. Next slide. So as of now, we are working on the various communication protocols that would like to use inside the pod and also the wireless modules that would like to implement for the pod and external control. For the in-pod communication, we are using CAN communication, and for the external pod, we would be using Bluetooth module. So this is a basic schematic of what are the functions that the navigation control department is working on. And as you can see, there's an emergency states. So that basically gives us the pod states from which, in case of any emergency, we'd be going into that state. Next slide. Now moving on to power systems. So this is responsible for the energy supply to all of subsystems of the pod. And this includes both the high power and high voltage and low voltage system. So basically it's divided into three parts: accumulator, battery management system, and power converter. As of now, we are mainly focusing on the accumulator and battery management system. The accumulator specifics is 400 volts, 100 ampere. And at the present stage, we are designing the total accumulator case. The stack configuration is 10s2p. For the battery management system, we'll be using master slave topology, and we are working on the master board as of now. The slave board has been designed, and we prepare to test it in the coming month. Next slide. So I'd like to hand over to the next team member.
So coming on to levitation, levitation is the newest addition to to our team. And while we were searching for the optimal levitation systems for our Hyperloop pod, we considered three alternatives: hybrid electromagnetic suspension, electrodynamic suspension, and the electromagnetic suspension. Next slides, please. After thorough evaluation, we have chosen to advance with the electrodynamic suspension system as of now. This is the simulation video we have simulated for the various design purposes of our EDS. Next slide, please. This is a testing video of our EDS. EDS system basically operates by flowing alternating current through coils, which induces the formation of eddy currents in a conductive plate, generating a powerful levitation force. The interaction between the induced currents and the magnetic field results in a stable and contactless levitation effect. The controlled application of AC current through coils enables precise management of the levitation force, ensuring a smooth and stable ride. And I would like to conclude that this choice aligns seamlessly with our goal of creating a high performance, reliable and energy efficient levitation system. Thank you. Moving on to the mechanical.
Yeah. So, like, we all know why we need brakes, and we'll be achieving this through two ways. Our objective is to design a mass efficient braking system. Firstly, to bring it from a high speed to a low speed, and then we would be using another braking system uh, to bring it from a low speed to a standstill. So we would be using magnetic brakes to reduce the speed of a pod from a higher speed to a lower speed. This would work on the principle of Lenz's law. We would be generating eddy currents in the I-beam, and this would resist the motion of the pod. And once the pod has achieved a lower speed, we would be using friction brakes to bring it to a standstill. So the purpose of using two different systems is to reduce the wear and tear that is caused due to frictional braking. Now moving on to VD and suspension, vehicle dynamics and suspension. Our objective is to design and develop a suspension system for the pod that would help, that would stabilize it despite the various disturbances that it might encounter, and keep the pod, provide a stable platform for the levitation and the power module, despite various motions like pitch, heave, roll, or yaw. Uh, we would have a lateral control module that would keep the pod stable under lateral movements, roll or yaw. So how we are going about designing the suspension system is that firstly the track won't be like a single large piece of uh, aluminum beam, right? It would have many sections. So whenever the pod goes from one section to the another, it might encounter some disturbances. So what we are trying to do is that the natural frequency of the suspension of the pod should not match the frequency of those disturbances that it might encounter to prevent resonance. So how we are going about achieving this is that we would build a two-layer chassis. We would have a stiffer suspension system between the track and the bottom layer of the chassis to maintain the tight clearances that the levitation and the LIM need. And then we would have a softer set of springs between the bottom part and the top layer. The top layer is like the main pod where people sit and the accumulator is housed. So the reason behind putting this softer set of springs between them is to provide comfort, uh, because the stiff suspension has like a natural frequency over 40 hertz, and comparing that say to a normal passenger car, the natural frequency of a passenger suspension system of a passenger car is between 1 and 2 hertz. So like a 40 hertz stiff frequency of 40 hertz would be very stiff. So it won't be very comfortable, which is why we are using a softer set of springs between the top and the bottom layer to provide comfort. So now chassis.
So hello everyone, I am Amrita, part of mechanical team at Infinity Hyperloop, and here I will be sharing progress report of our chassis and aeroshell. So let's start with chassis. So idea of chassis is is to provide a base frame of our pod, and it says don't force pieces that doesn't fit. So we need chassis to integrate the whole pod. Chassis provides ease of assembly and disassembly. It also distributes load and stress evenly and provides strength to the structure. Next slide, please. So in the previous iteration, we made a C-shaped chassis and used aluminium plates. We welded all the plates together to make chassis. And for this iteration, we will be using two-layer chassis, which will be manufactured by carbon fiber, and we will be using a frame chassis. So that was all about chassis. Now let's move towards aerodynamics department. So here our task is to design a low drag coefficient aerodynamic shell for Hyperloop pod. So next slide, please. Now let's talk about what we have done till now. So we have designed and simulated our pod, which looks like this, and also tested our material. And in simulation, we got some drag coefficient, which was good enough for our dynamics in that iteration. So we choose glass fiber after testing various materials to manufacture this structure of aeroshell. Next slide, please. Here is some glimpse of manufacturing of aeroshell by our team. Here you can easily see that we are using glass fiber and we are doing layup manually. And we manufactured this aeroshell in around 1 month. And for next iteration, we will be using carbon fiber. And that was all about our pod. And now I would like to hand over this meet to next person for further discussions. Thank you.
So that was all the technical aspects of our pod. And lastly, we would like to thank our sponsors. So next slide, please. And our platinum sponsors, IIT Delhi and S-Chan Group, for supporting us, and all the industries who aided us in this project. And thank you. And we are open for questions now.
Thank you very much, Ria and the whole team. So for questions, you guys can raise your hand or type in the chat. Let me check the chat. Okay. Yes, go ahead. Vivek.
Yeah, hello, I'm Vivek. I wanted to ask that what's the air gap that you are planning to use for the levitation and propulsion system?
So
Hello.
currently for the propulsion.
Yeah, hello. Actually, for the propulsion system, we are having an air gap of 2 mm and the track width of around 6 mm. So total of 10 mm actually. Like if you see the whole air gap, like it was a double-sided linear induction motor. And for levitation, actually, we have not decided. Actually, levitation system is in progress. So like we will be deciding it at the like after further testing of the levitation system. So this was only our linear induction motor was complete as far as.
Yeah, okay, thank you.
Thank you.
I can ask a question. Guys were talking about braking. Do you guys have any idea when is the friction brake? At what speed range the friction brake will start braking?
Actually, we have decided it to be around 10 meter per second. So.
Okay. All right. Any more questions? Okay, then thank you very much, Hyperloop Infinity team. That was very interesting.